Good afternoon, professors. I'm Tim, and today I'll be presenting our machine learning project on default prediction for American Express, or Amex for short. The Amex dataset contains 190 columns, including 2 indexing columns consisting of customer ID and transaction date time, 11 categorical features, and 177 numerical features. The goal of this project is to predict whether a customer will default based on their transaction history. For evaluation, we use the Amex metric, which is defined as half of the sum of the normalized Gini coefficient G and the default rate captured at 4% D. Preprocessing was carried out with reference to Radars notebook. The data was first converted to smaller data types to reduce memory usage, and floating point values were rounded to 2 decimal places to remove noise. Next, feature engineering was performed by aggregating data for each customer. For S2, the datetime variable, we took the count, representing the number of transactions. For categorical data, we aggregated the number of distinct values and the last recorded value. For numerical data, we computed statistical summaries such as mean, standard deviation, minimum, maximum, and the last recorded value. This slide shows the code used for feature engineering. The S2 and categorical features were aggregated inside the cat feature function, while numerical features were aggregated inside the num-features function. Next, we'll discuss the machine learning model used in our project: logistic regression, k-nearest neighbor (KNN), multi-layer perceptron (MLP), light GBM, and extreme gradient boosting (XGBoost). For logistic regression, we use a 80-20 training validation split to establish a baseline performance. The training data was fitted and transformed, while the validation data was transformed for prediction. The same process was repeated for the test set using the entire training data for model fitting. The k-nearest neighbor model followed a similar methodology to logistic regression, but included principal component analysis (PCA) for dimensionality reduction. We set n components to equals to 0.5, meaning PCA retains enough components to explain at least 50% of the total variance, helping to reduce computational costs. For multi-layer perceptron, we use a simple architecture. The categorical and numerical features will each pass into 2 separate 3-layer sub-networks. The outputs, along with the S2 transaction count, will then combine and pass into a final sub-network with 2 hidden layers to produce the logics or the probabilities. To improve stability, we use ensemble learning by training 5 MLP models with 0 through 4 and average their prediction. Next, we use Light GBM, a gradient boosting framework developed by Microsoft. It was chosen because it can effectively handle a large-scale dataset, making it suitable for our case with hundreds and thousands of rows. Unlike traditional gradient boosting algorithms that grows tree level-wise, Light GBM grows tree leaf-wise, allowing it to reduce loss more effectively and achieve higher accuracy. For Light GBM, we tune 2 main hyperparameters: num-leaf, which controls the complexity of the tree, and max bin, which determines the number of bins that continuous features are bucketed into. Both parameters help improve model accuracy and control overfitting. For our final model, we use num-leaf to be 64 and max bin to be 255. We also applied ensemble learning by training 3 Light GBM models with seeds 42, 52, and 62 and averaged their predictions. Lastly, we implemented XGBoost, a popular gradient-boosted decision tree algorithm widely used for structured data. The model combines many small decision trees trained sequentially using gradient descent to minimize the loss function. We tune only the maximum depth parameter, which controls the complexity of the tree and helps prevent overfitting. For our final model, we use max depth of 10. Similar to Light GBM, we use ensemble learning with 3 XGBoost models, training using seeds 13, 67, and 77, and average their predictions. This table shows our private and public leaderboard scores for our Kaggle submissions. The KNN model performs the worst, followed by logistic regression and MLP. The 2 best performing models were Light GBM and XGBoost, both achieving private scores of above 0.8. Now, moving on to our model evaluation. For logistic regression, the lower metric score can be explained by 2 factors. First, the imbalanced dataset. With roughly a 3-to-1 ratio of non-defaulters to defaulters, this allows the model to achieve a high overall accuracy simply by predicting the majority class. Second, logistic regression struggles to capture non-linear relationship between features, which limits its predictive power. For KNN, the performance was affected by the curse of dimensionality. In high-dimensional space, the concept of nearest becomes less meaningful, as distance between points tends to become uniform. This reduces the model's ability to distinguish between similar and dissimilar observations, and also increases computational complexity significantly. Finally, for MLP, the lower performance compared to gradient boosting models can be attributed to several reasons. MLPs are sensitive to feature scaling, and normalization may have led to some loss of information compared to using raw values. Additionally, given the large number of input features, from 179 to 908 after transformation, the relationship became highly nonlinear, which gradient boosting models handle more efficiently. Lastly, since the dataset were anomalized, spatial and sequential patterns were lost, limiting the MLP's ability to capture complex feature interaction. Moving on to the evaluation of our final model. Our final model was an ensemble of XGBoost and LightGPM. The ensemble achieved the highest Amex matrix score, primarily because both models are tree-based learner that split data based on threshold values. They are largely invariant to transformations such as min-max scaling or normalization, meaning they require minimum preprocessing compared to neural models. Individually, both models already perform strongly, each achieving an Amex matrix above 0.77 even without fine-tuning. Despite both being gradient boosting algorithms, they operate independently and differently. LightGPM goes tree leafwise, allowing deeper exploration in areas that reduces loss the most, while XGBoost grows tree level-wise, maintaining a more balanced structure. This methodological difference, along with the distinct regularization, sampling, and split finding strategies, mean that the two models learn complementary decision rules. As a result, combining them produce better generalization than either models alone, with low engineering overhead and quick deployment. We fine-tuned the ensemble weights between XGBoost and LightGPM, achieving a public Amex metric score of 0.79995. Our LightGPM model alone achieved a private score of 0.80715, placing us within the top 10 percentile on both leaderboards. This demonstrates a strong generalization ability of our ensemble and validates the effectiveness of the gradient boosting models. Next, we encountered several challenges during this project. First is the anonymous feature. Since all features name were anonymized, it was difficult to perform meaningful feature engineering, and we had to manually explore combinations of important features to uncover useful patterns. Next is the high dimensionality. After feature engineering, our dataset expanded to 908 features, which significantly increased training time and reduced model interpretability. Third is the imbalanced dataset. The dataset had a 3-to-1 ratio of non-defaulters to defaulters. This imbalance made accuracy an unreliable metric, since a model predicting non-default most of the time could still appear as highly accurate. Lastly is the competition dynamic. In Kaggle competitions, many participants engage in reward hacking, submitting hundreds of slightly modified ensemble weight combinations to optimize the Amex metric. This led to a dense cluster of top scores with minimum score differences. We also had to submit over 100 entries before finalizing our best leaderboard position. Despite these challenges, we were still able to achieve competitive results and gain valuable insights into handling complex, high-dimensional financial data. With that, I'd like to end off our presentation. Thank you.